Alright, welcome back everyone. In this video we're going to talk about the derivative of exponentials, specifically exponentials in the form e to the x, and we're going to talk about why they have the derivative that they do on a conceptual level. So I'm going to just jump right to the punchline, and the main thing here is that if we have a function f that is equal to e to the x, then the derivative of f is also e to the x. So e to the x, where e is Euler's number, is this special function that is its own derivative. So we've talked about e in the past. It's this sort of magical number of sorts, and the reason, or one of the reasons it's especially magical, is that it has this property that it is its own derivative when we have the function e to the x. So let's take a look at the graph and talk about why this might be happening. Remember, the derivative is the slope of the tangent line. So when we have the derivative f prime, that formula, that function, tells us the derivative or the slope of the tangent line at any input value x. So let's look at some tangent lines of the function e to the x to determine what the derivative is. So to determine the slope of those tangent lines to help us understand what the derivative will be. So if we start at x equals 0, I'm seeing that the output is 1, and we can check this with the formula. So we put 0 in, we have e to the 0 power, which anything to the 0 power is 1. And if we look at the tangent line at this value, I'm seeing that the slope is 1. We go up 1 to the right one, up 1 to the right one. Now we can take another point. Let's try at x equals 1. The output here is e to the 1, which is just e, which is about 2.71. That's Euler's number. Then if we look at the tangent line at this point, I'm seeing that we go up a little less than 3, maybe 2 3/4, and we go over to the right by 1. So we go up 2.75 over by 1, so the slope is around 2.75. Let's also try a tangent line at x equals -1. So when we plug -1 in, we substitute it in, we get e to the -1. That's 1 divided by e, which if I do that on my calculator, I'm getting 0.37. Now if I draw a tangent line at -1, I'm seeing that we go up 1 over about 2.5. So that's 1 divided by 2.5, and again, calculating that, I'm getting about 0.4. So if we look here and we compare the output values to the slopes at those points, so we look at the output, the function, and the slope, which is the derivative, I'm seeing that they're almost the same. I have 1 and 1, I have 2.71 and 2.75, which remember those were just estimates, and then I have 0.37 and about 0.4. Again, that 0.4 was just my estimate looking at the graph. So we can see that these are basically the same number, and this is telling us something really unique. Specifically, it's telling us that the slope of the tangent line is the same as the function values. Alright, so let's take a second and talk this through. So what we've seen so far is that when we take an x value and we look at the y value that goes with it, that y value is the same as the slope at that point. So we're saying that the function and the derivative, the output and the slope, are the same at every value x. I think that this becomes a little more obvious, and at least it's easier for me to understand if I look to the left side of the graph. As we go to the left, the outputs approach 0, and the graph is sort of flattening out. It's getting flatter and flatter and flatter. So the slope is approaching 0. Since it's getting flatter, it's getting closer toward horizontal, and the outputs are getting closer toward 0. So the outputs and the slope are both approaching 0 as we go to the left side of the graph. You could also make a similar argument when you go to the right side of the graph. So as the output values get further away from 0, they get to be larger numbers, the slope is getting steeper. So the slope, or the derivative, is also becoming a higher and higher number. So it sort of makes sense that maybe e to the x, when we look at its graph, its derivative would have a very similar shape. And that's the conceptual understanding I'm trying to emphasize here. And so our conclusion at this point is that the slope of the tangent line at x equals a is approximately the function value at a, so f of a. This means that the derivative at a is approximately the function at a. And this turns out to be true. So the derivative at a is actually equal to the function value at a. So these are equal for all values x equals a. This involves a proof that requires some more complicated techniques that we don't have yet, but we will do this later as a way to reconfirm what we know now. So this means that if f of x is equal to e to the x, f prime is equal to f of x. The derivative is equal to the function in the case of e to the x. So this is a lot of words just to say that e to the x is its own derivative. The function and its derivative are the same when we have e to the x. Alright, so that isn't a formal proof for why e to the x is its own derivative, but I'm hoping this gives you a little bit of understanding about why it might be true, and hopefully you can believe it at this point. Again, when we have more advanced techniques, we can prove this outright, but for now we're just going to take it as true that e to the x is its own derivative. The derivative of e to the x is e to the x. Thanks so much for watching, and I will talk to you in the next one.